Okay, that's fine.
Okay. So, Paul's still being. Okay, so yes, welcome back to the slightly delayed second talk of this session. So it's very nice to welcome Sheel Ganatra as our next speaker. He's going to tell us about functoriality and sheaf-theoretic properties for warped Fukaya categories. Let's welcome him.
Thank you very much, and I'd like to start by thanking the organizers for the invitation to come to this wonderful conference and present our work. The title of my talk is Functoriality and Sheaf-Theoretic Properties for Wrapped Fukaya Categories, and the goal of my talk is to describe, give some overview of the theory of Liouville sectors and their functorial wrapped Fukaya categories, following specifically a paper written in joint work with John Pardon and Vivek Shende called Covariantly Functorial Wrapped Fleur Theory and Liouville Sectors. But also I want to say words, we wrote a series of 3 papers, and that's the first of our papers. I'll call that GPS 1 in this talk. And I want to talk about some further developments after this paper as well, including our further 2 papers, but also some new works. So that's the goal of my talk. I want to start by setting up some geometric preliminaries. Where's the setting in which these structures are being studied? So I don't want to assume anything about that. So our setting that we'll be working with is a setting in symplectic geometry called the setting of Liouville manifolds. This is a certain class of exact and in particular non-compact symplectic manifolds. So exact just means the symplectic form is exact, but the Liouville condition is something more. It's some sort of convexity at infinity condition. It can be phrased as saying if you take the Liouville vector field, that's the vector field that's symplectic dual to the 1 form, which is the primitive of the symplectic form. Then that Liouville vector field presents your Liouville manifold as some compact piece, union a cone over the boundary of that compact piece, where Z is outward pointing along the boundary of the compact piece and generates a complete flow out to infinity. We focus on a special subclass of Liouville manifolds called Weinstein manifolds. And these are symplectic Liouville manifolds for which the Liouville vector field is gradient-like for a Morse function. This is a very broad class of non-compact symplectic manifolds. It includes many examples of interest from algebraic geometry. For instance, all smooth complex affine varieties fall into this class. It also includes cotangent bundles, which are among the first symplectic manifolds one studies, and more generally, all Stein manifolds. So the symplectic geometry of this class of manifolds has been widely studied. For instance, there's now a comprehensive textbook on the geometric constructions involved in Weinstein manifolds by Chilebach and Elias Berg. And there are cohomological invariants that are frequently used to tell such manifolds apart in the symplectic category. And the most frequently used ones fall into this broad umbrella that I'll call wrapped Fleur theory. And they encompass 2 types of invariants. One is a cohomology theory for symplectic manifolds called symplectic cohomology. Another is a categorical invariant for symplectic manifolds called the wrapped Fukaya category. And these are really, I'll call them in the terminology of string theory, closed string versus open string invariants. They're sort of 2 invariants that are closely related. They're not independent of each other. There's some sort of open-closed string relationship that gives you symplectic cohomology from the wrapped Fukaya category. So while the symplectic cohomology is maybe a simpler cohomology theory, in principle it's recoverable from the wrapped Fukaya category, which will be the primary object of study for us today. I won't yet define it. I'll spend a little bit of time on saying broadly what that is a little bit later. But I want to make a remark that these invariants are analytic invariants. As in Tobias's talk, they're defined via some sort of elliptic PDE. You're counting solutions to some sort of Cauchy-Riemann equation on your symplectic manifold, and they are difficult to compute directly as a result. The wrapped Fukaya category also appears in Konsevich's homological mirror symmetry conjecture as a mirror counterpart to categories of coherent complexes on varieties which need not be smooth or proper. So on such varieties, categories of coherent complexes have infinite rank X groups. And one of the reasons these so-called wrapped Fukaya categories were introduced was to allow for infinite rank X groups on the symplectic side. Okay, so these are the broad remarks as the setting of what we'll study, and a basic goal is to find tools for computing these and structural properties of them, which reduce them to more topological type computations. And in that vein, there was an important conjecture made by Kontsevich in 2008, which is a major motivation for our work. So Kontsevich's conjecture involves studying for a Weinstein manifold this gadget, which I'll call bold L. It's you might call it the core of X with respect to Z. You could think of that as the union of all descending manifolds from critical points. So you take your Liouville vector field, it's a gradient-like for a Morse function. So in particular, there are critical points or zeros of it. There are finitely many. And you take the union of its descending submanifolds. Here's a picture of such an L on such an X. This is always a half or less dimensional CW complex, which is homotopy equivalent to the original space. And in fact, it sort of has some Lagrangian or isotropic properties. Then the proposal of Kontsevich is there should exist a co-sheaf of categories on L whose global sections give W of X. So what do I mean by that? Well, by co-sheaf of categories, I really just mean the dual thing to a sheaf of categories. So for every open set on this Lagrangian skeleton, I should associate some small category, and it's covariantly functorial with respect to inclusions. And global sections, taking global sections is some sort of co-limit process. You should think of by analogy, the Van Kampen formula. It's some sort of Van Kampen formula for gluing together local pieces. And moreover, the local pieces should be simple in favorable cases. And so if you combine these two facts that were present in this proposal, you would obtain a combinatorial presentation of wrapped Fukaya categories. So this will give us a very powerful computational tool. Okay, so for a minute before I talk about our work, I want to just say what the idea behind this proposal was. And the idea was something like this. So if we start with an open subset of the skeleton, maybe that open subset is so here's a skeleton. It's some sort of graph or ribbon graph with two trivalent vertices. Okay, so let's start with an open subset that looks like this. Some open subset of this the top trivalent vertex. The idea is we should be able to associate to that some sort of piece of the entire symplectic manifold, just roughly by flowing down to it or by flowing up from it. Okay, so the piece will look something like this. Okay. And I'll call this piece XU. It's some sort of nice symplectic subset where I haven't defined what I mean by nice. But whatever I mean by nice, it should mean that the symplectic subset has a well-defined functorial in U local Fukaya category associated to it. And moreover, now if I can build all these local Fukaya categories for these subsets associated to pieces of the skeleton, then I can also try to check whether these local Fukaya categories patch together and satisfy descent and give us the global Fukaya category. Okay, the first observation is such a nice symplectic subset cannot be a Liouville manifold in the sense above, roughly speaking, because of these blue lines. Okay, there are sort of some new class of boundary along which the Liouville vector field doesn't sort of point outward and generate a complete flow. So we leave the category of Liouville manifolds and we have to enlarge the category. And this is what the theory of Liouville sectors is about. So a rough overview of our work is that it realizes some version of Kontsevich's conjecture that doesn't really depend on skeletons. We focus on the theory of these nice symplectic subsets, which we term Liouville and or Weinstein sectors, and develop their local and functorial wrapped Floer theory. Because that's really the content of our first paper, and I'll spend a lot of the time today telling you about that. But let me also just give you a quick overview of what happens in the two subsequent papers in our series. In our second paper, which is titled Sectorial Descent for Rapid Fukaya Categories, we proved this descent formula, or this co-sheaf formula for rapid Fukaya categories associated to suitable coverings by such Weinstein sectors. And along the way, in order to prove that, we actually need to develop an array of structural tools for rapid Fukaya categories which might be of independent interest, such as Kunith formula and some way of computing information about functors. And then our third paper applies this further to compare rapid Fukaya categories to purely topologically defined categories called categories of microlocal sheaves. These were, as introduced by Kashiwara Shapira. The particular proposal we implement was introduced by Nadler. And these categories are already co-sheaves on the Lagrangian skeleton, whose local stocks can be often combinatorially presented. So in particular, we do deduce as a result combinatorial formula for a broad class of Fukaya categories. So before I develop the theory, I just want to give you an example of the types of creatures we'll now allow without talking about skeletons. So here's a Liouville manifold on this side. It's a 3-punctured torus. And now what I'm going to do is draw cuts along it. And so this is going to be an allowable class of cuts for my theory. I'll draw these. I'd call them sectorial cuts or sectorial hypersurfaces. So in this dimension, a sectorial cut or hypersurface is just a properly embedded cylindrical, meaning tangent to z near infinity, copy of the real line. So I can just cut by a one-dimensional manifold that's R, properly embedded. It can't cut by any S1s. That's important. So trying to cut like this would not be allowed. Okay, so I introduce these cuts, then I actually cut my Liouville manifolds. Now I get pieces which aren't quite Liouville manifolds. They have some sort of non-compact directions, these boundaries at infinity, but they have these new actual boundaries, these blue boundaries. Okay, and these are all Liouville sectors. And by thickening up the cuts a little bit, I can sort of realize these cuts as giving me a covering, right? So I can just think of these two Liouville sectors as being glued along a thickening of the line I cut out, right, which is a strip. It's another Liouville sector, and then same over here and over here. And so this should be an allowable covering of Liouville sectors, and such a covering should give me, I should have functorial local Fukaya categories and a local to global formula for the rapid Fukaya category of the total thing from the pieces. For those of you who are interested in mirror symmetry, maybe I'll just make one comment while we're here, which is that if I think about the mirror to this picture, it's relatively well studied. The mirror to a 3-punctured torus is a thrice nodal elliptic curve like this. Okay, and each of these pieces. So now I decompose my 3-punctured torus into each of these pieces, and these standard pieces, which look like cylinders with two extra blue boundaries, these are each mirror to CP1s. Okay, maybe I should say the rap Fukaya category of this is the co-limit of the rap Fukaya category of these. And then these strips, there's a stabilization property that's true for rap Fukaya categories. So a strip is essentially, something like some contractible space or something. So it has the rap Fukaya category of a point. Okay, so and so this matches coherent sheaves of a point. Okay, so in other words, the decomposition I wrote down here is mirror to the decomposition of this coherent sheaf, this triply nodal elliptic curve into 3 P1s. Glued along a pair of points each. Okay. Okay, glued along 3 points rather. Okay, so this is just a picture to have in mind as we go through definitions. Okay, so I'll now spend some time talking about actually what Liouville sectors are and how to think about them. So what are the new target geometries we introduce? So sectors are the gadgets I want to focus on, but I'll take a detour through this theory of stops, which are, it's easier to say what they are. That's one of the reasons. So stops were also earlier studied by Roux and Sylvan. So a stop is just a pair of a Liouville manifold and some closed subset at infinity. So all I do is I take whatever Liouville manifold I was interested in before, and I can put some data at infinity. Okay. If the data I put is a codimension 2 Liouville hypersurface, so it's Liouville of dimension 2 smaller than the original x, then I call that a Liouville stop. And a Liouville sector can be obtained from a Liouville stop by removing some neighborhood of this Liouville stop. So it's any target of the form Liouville manifold minus a neighborhood of a Liouville hypersurface, where this neighborhood is a standard neighborhood of the form y times half plane. I'll draw some pictures of this to give an idea for what this is. Let me just go right here and do that. So, for example, I'll just focus on one of these two examples. If I start with this example on the bottom, I take the Liouville pair C with 3 points at infinity. The way I should get the associated sector is I should cut out these half-plane neighborhoods of the 3 points, and what's left is this blue region here, which I can draw in this way. Okay. And one of the reasons I might like to think of having a sector is this sector, it's easier to embed this sector into sort of other Liouville manifolds of interest. Sectors have a little bit more evident functoriality, and in terms of, there's a sort of wide class of inclusions of Liouville sectors. For instance, this sector, which we sometimes call the A2 sector, it embeds naturally into this pair of paths. Okay, so now if I remove a y cross half-plane neighborhood, in particular, the boundary of the resulting W is of the form y cross R. So that's the higher dimensional generalization of the fact that I was only allowed to cut by R's in dimension 2. So we could also intrinsically study some sort of a definition of Liouville sectors where we take a Liouville manifold with boundary satisfying some conditions. Okay? And that will imply that the boundary has to be y cross R. So in fact, in our paper, that's the way we focus on Liouville sectors is sort of through this definition, technical definition that I've omitted for simplicity today. So actually, we can go back and forth between Liouville stops and sectors, Liouville stops and sectors rather. So given a pair xy, as I mentioned, the sector is x minus a neighborhood of y. But then given a sector, we know that the boundary of the sector has to be of the form y cross r. So I can then just attach back y cross half plane along y cross r and get back my Liouville pair. This is a process called convex completion. So we can go back and forth, they're equivalent. Therefore, you might say, well, stops are more general because I can have non-Liouville stops. And indeed, that's true. However, sectors, as I mentioned earlier, have this more evident functoriality, which is what the focus is for our first paper. Okay, so I did these examples already. So let me tell you a little bit about the wrapped Fukaya category of a Liouville sector. So this is a categorical invariant, chain-level categorical invariant of a Liouville sector in the sense of it being an A infinity, or you could think of it also as a differential graded category. It has as objects Lagrangian submanifolds, okay, which are half-dimensional submanifolds of our 2n-dimensional manifold, which along which the symplectic form vanishes. They should be exact Lagrangians, which is a condition with respect to the lambda I fixed on my original Liouville manifold. So lambda restricted to L should be exact. They're allowed to be non-compact, but they have to be properly embedded and cylindrical at infinity. Then they live in W, but they never touch the boundary. Okay, that's the key point. So they live in W, but don't touch the boundary. The morphisms between a pair of such Lagrangian submanifolds are cochain complexes, and I won't get into the full cochain level definition, but I'll talk about what is the cohomology. So the cohomology is an invariant, also sometimes called wrapped Floer homology or wrapped Floer cohomology of the pair KL, and it's defined from ordinary Floer cohomology. So we start with ordinary Lagrangian Floer homology, or cohomology rather. I'm just going to treat that as a black box, but let me just say the ordinary Floer cohomology HF is a chain complex generated by intersection points of a pair of Lagrangians, and the differential counts some holomorphic disks and cancels out intersection points if there's a disk between them. Now, what I do is I don't take any given HF of KL. What I do is I take some direct limit of HF of KLs, or rather of HF of K plus Ls, where K plus is a so-called positive at infinity isotopy in W, not touching the boundary of W. Okay. So we call such an isotopy a wrapping of K. And let me just, I'll draw a picture saying what this is in a second. Yes, question? Yes. Yeah, cotangent fiber of a point's a perfectly fine object, basically. Thank you for the question. I appreciate the clarification. So a Liouville sector has two types of boundaries. Okay, one is a boundary that's actually at infinity. It's not a boundary. It's like some limit at infinity. So we call that the boundary at infinity. Okay, and then the other, well, in this case, there's no sector boundary. So in this case, sector boundary is empty. Okay, and what we're not allowed to touch is the sector boundary. So did you remember those blue cuts I drew? We're not allowed to touch the blue cuts. We're allowed to touch the dotted boundaries, if that makes sense, or limit to them. So the blue cuts behave like barriers. We're not allowed to touch them. We're not allowed to cross them when we flow our Lagrangians. That's one reason the prefix partially sometimes appears. We're sort of doing something, but we're blocking our ability to do something with these blue cuts. Okay, so was there another question, actually? Okay. So the basic observation I'll say is that there's at infinity there's some asymmetry. So there's this boundary at infinity of our Liouville manifold. It's a contact manifold, and it's naturally co-oriented. So it has a natural positive directional half space. So when I look at flows, isotopies of a given non-compact Lagrangian that move at infinity, I can talk about whether I move in a positive direction or not. I can ask, do I move positively or do I not? And I'll focus only on isotopies that move positively at infinity. And the key observation is if I move positively at infinity, there's a map from HF of KL to HF of K plus L, which is what the maps in this direct system are, which is what allows me to take a direct limit. Okay. These maps may not be isomorphisms. So Floer cohomology for non-compact Lagrangians is not an isotopy invariant. So this is some way of repairing that. That might be one way of thinking about this. Okay, we can also define partially wrapped Fukaya categories of stops. Instead of avoiding the boundary of W, we avoid the stop. That's the basic distinction. Okay, and if I start with the Liouville pair or take the associated sector, I get the same category. Okay, let's just quickly step through one example of what this looks like. So here I'm going to start with the Liouville sector I get by starting with T star S1. and I take one point on one side of infinity and remove a neighborhood of it. So I get this blue sector boundary. And I'm going to look at the cotangent fiber, this green cotangent fiber, and I want to compute this wrapped Floer cohomology in this sector of L with itself. Okay? So what I'll do is I'll start moving L positively, but not allowing it to touch the blue boundary. So I've drawn for you the positive directions. Those are the red arrows in this picture at infinity. So I'm allowed to move. So what happens is, okay, let's move by a little bit. That's perfectly fine. I get this purple Lagrangian L plus epsilon. Now let me keep flowing at infinity. And what's going to happen very quickly is on the top boundary, my Lagrangian just gets stuck. It runs into this blue boundary that I'm not allowed to touch. On the bottom, I just keep flowing in an unbounded fashion. I just keep winding around and around the circle. So here's, you might call this L plus. This is a particular positive wrapping that ends up like this. And then here's L plus plus. Okay, and then I can keep going. Okay. And so I get all these intersection points, and I can label the intersection points by some elements, by just some formal labels, but they will turn out to not be so formal in the end. So I'll label this intersection point 1. I'll label this intersection point Z, and I'll label this new intersection point of L plus plus with L Z squared. So I'm not going to verify all the details, but there's no differential here. So this chain complex of intersection points is cohomology. Okay, so for some pi1 reasons, there can't be holomorphic strips. And then in the continuation maps between this complex and that complex, 1 is sent to 1 is sent to 1, Z is sent to Z, and so on and so forth. So what we get as we take the limit is that this wrapped Floer cohomology of L with itself is, at least additively, it's polynomials in Z with whatever coefficients we're using. For instance, here I'm using complex coefficients. But in fact, more is true. This is actually true as an algebra. Okay? So this is not just true additively, it's true as an algebra. I didn't verify that for you, and I won't right now. But there's some way of putting an algebra structure on this, which is part of the wrapped Fukaya category. Yes. So if you remove the stop upstairs, you get C adjoins ZZ inverse. So we're starting to see the mere rings of functions to A1 or to GM. Okay, so let me tell you a little bit about just a select technical detail in how we define the wrapped Fukaya category of a sector W. There's one new challenge that we run into as opposed to the definition for Liouville manifolds. And this is the primary thing, but there are a number of other details, but probably this is the newest. And the main challenge is that when you study, you try to define counts of holomorphic disks. You want the counts to be compact so that there's a well-defined finite count and you can just get the number. The problem is now we have a space which is, first of all, it has a non-compact end and it has a boundary. And if there's a sequence of disks in the moduli space of maps that tend to the boundary or tend to infinity, it can break compactness. It can break the properties we want. So we need to prevent, and the new type of thing we need to prevent is holomorphic disks tending to this new sector boundary. Okay, but we also need to prevent them from tending to infinity as before. So disk confinement, so the basic thing we do is we establish some disk confinement results for a class of complex structures which suffice for our purposes. And actually disk confinement is also a key step in this functoriality result that we show in this paper. If we have an inclusion of sectors, the way we get functoriality for our wrapped Fukaya categories is as follows. There's this basic diagram. Okay, so I start with the wrapped Fukaya category of W1. Let me draw a picture of W1 and W0 in it. Maybe here's W1. Here's W naught. Okay, so what I can do is there's some intermediary between W naught and W1, which I'm going to call W sub supported in W naught, wrapped in W naught of W1. In this category, what do? I look at Lagrangians in W naught. Okay, so I only look at Lagrangians like this, that are in W naught. I only take the direct limit over wrappings in W naught. I don't allow myself to cross W naught. So I only allow myself to do things like that. But when I'm taking my Lagrangian Floer cohomology and counting disks, I allow my disks to live in W1. Okay? And this category has an almost tautological map to the Fukaya category of W1, which is just called wrap more. Include a direct limit over a smaller collection of wrappings, the ones in W0, into the larger collection of wrappings. But, all the disk counts are the same in the sort of subsystem of the direct system of morphisms, and the objects are a subset. And so disk confinement, if one has a disk confinement result, then you learn that this category is actually the Fukaya category of W0. Disk confinement would tell us that the disks, this means that the disks that a priori could go into W1 stay in W0. Okay, that's a sort of a priori statement. Okay, so that's basically a quick recap of how we get functoriality for Fukaya categories. I want to spend my remaining time, about 10 minutes, telling you about some recent applications. So after we developed functoriality, we also developed this sheaf property for Fukaya categories. I won't talk about our proof of that in more detail now. I just want to maybe switch gears and talk about recent applications. But I'll pause for a minute for questions if there are any questions. Yeah. Yeah, so the condition for the boundary of the sectors, I didn't say it actually. I just said the boundary of the sector has to be the boundary obtained by removing a standard neighborhood of y cross half plane. But there's a technical condition on the boundary which implies, so the geometric underlying condition, we require more, but the underlying condition is the boundary splits as y cross r symplectically. So the characteristic foliation on this codimension 1 hypersurface is just an R action. Question? If you delete this condition, then your Lagrangians wrap into W1, and you're computing the morphism spaces here. Right? So in the wrapped category of W1, what we're doing is we're taking the limit over wrappings of K that are positive in W1 of HF of K plus K. So K plus L rather. So we're allowing, this. If we start with this Lagrangian, we'll allow it to wrap like that, to start wrapping around the circle. Like that, right? It'll start to wrap in this global W1. It'll no longer, it'll be something interesting. It'll compute morphisms in W1. Yeah. Question? Near the boundary, we want the boundary to be of the form y cross r. But there's a little bit more technical condition we impose at infinity. So maybe I'll omit it right now, but I'm happy to talk about it after the talk. Okay, so maybe I'll spend just a few minutes talking about some recent applications of the theory of sectors and some interesting things one can do with it from a computational standpoint. So in a paper of mine joint with Hanlon, Hicks, Pomerleano, and Sheridan that came out earlier this summer, we used some of the theory of sectors to give a recent proof of Kontsevich homological mirror symmetry conjecture for a large class of Bacharev mirror pairs. These were mirror pairs put forward by Bacharev in '93 of compact Calabi-Yau hypersurfaces in Fano Ys. In toric Fano Ys. So maybe I should say. And to explain how this is an application of the theory of sectors, well, it wouldn't even seem to be the right target geometry, because I mentioned we should work with Liouville manifolds or Weinstein manifolds, these non-compact things. But there's this famous classic idea of Seidel from 2002 that if you want to compute the Fukaya category of a projective Kähler Calabi-Yau, for instance, you should begin by removing an ample divisor. So in this case, if I have a Calabi-Yau hypersurface, the ample divisor I'll remove, and that we removed in our paper, was the intersection of the toric divisor with the hypersurface. So if you remove that ample divisor, you get a complex affine variety. And this is in particular Weinstein manifold. It'll be some Weinstein hypersurface in C star to the n+1. And in nice cases, you can study the compact Fukaya category of the of the compactification as a deformation in the sense of deformation theory the Fukaya category of this Weinstein manifold. But now some subtleties arise. The category we have very strong tools for computing is this larger wrapped Fukaya category. But the subcategory of objects that deforms well to the compact Fukaya category is the subcategory where I only allow compact Lagrangians. I don't allow any non-compact Lagrangians whatsoever. So we have very topological tools for computing this larger gadget, and one of the crucial steps in this work was to try to pin down this smaller subcategory of compact Lagrangians. So I should say there's work of Gamage and Shenda, which also applies this toolkit and comparisons with microlocal sheaf theory to compute this larger wrapped Fukaya category. And it establishes a version of homological mirror symmetry for the wrapped Fukaya category of this affine variety, this divisor complement. The form of homological mirror symmetry one gets is the wrapped Fukaya category is isomorphic to coherent complexes on a singular degeneration of the Calabi-Yau, the mirror Calabi-Yau. So you study the degeneration to the toric boundary divisor. So in the dual Fano, you look at the toric boundary divisor. That's a singular variety, and you look at coherent complexes on that. So our contribution was to compute the subcategory of compact Lagrangians, and then study the deformation problem and establish a sort of versality formula or versality result, which says that the space of deformations is roughly speaking canonical, and this gives a computation of the compact Fukaya category up to some change of coordinates, which is like a mirror map. So I don't want to say too much more about that right now, but the main thing I want to point out is we use this theory of sectors in a very crucial way to say what this subcategory of compact Lagrangians is. The point is we expect this subcategory of compact Lagrangians, in this case, to be mirror to perfect complexes, which sit inside coherent complexes of the singular variety. And so there's a characterization of perfect complexes on this singular toric divisor in terms of the ambient toric variety. So we use some sort of functoriality of homological mirror symmetry. So we have some sort of push forward functor on the algebraic geometry side, and we look at its mirror, and that's some sort of sector inclusion functor in the sense of our theory of sectors. And so we sort of compute some properties of that in order to pin down this compact Fukaya category. The other recent application I want to highlight was just a new computation of wrapped Fukaya categories of a wide class of complexified hyperplane complements. And these verify conjectures coming to us from representation theory by Lauda, Licata, Mannion. So this was not work of mine, but it was joint work of a current student of mine, Xiang Liu, with Sukju Li, Yin Li, and Chekyu Mak, which also came out this summer. And so here one's interested in a complexified hyperplane complement. So what I mean by that is we take c to the n, and we remove some hyperplanes cut out by real equations. And so here's a picture of the real part of it, of this hyperplane complement. I'm looking at everything outside of the purple lines. And so this hyperplane arrangement has some complexity. And what I'm going to do is introduce a bunch of sectorial cuts. Okay, so I'm just going to slice this picture by a bunch of hyperplanes, but now they're actually codimension one. There's a subtlety. Everything looks the same on the real part, but I'm going to cut by equations of the form real part of a linear function equals c. So it's sort of real codimension one, not complex codimension one. Everything looks the same here. And when I do, and I look at my pieces, inductively, the complexity's been reduced. So here, as I see, if I make all these cuts within any two, there's at most one crossing now, right? So I've looked at this configuration with many crossings of planes and reduced it to some picture with fewer crossings, and then I could try to cut it again. So this is the basic idea that's implemented in this paper. And then they use theory of sectors and this local to global formula to compute. Okay, well, let me stop there. Thanks very much.
Okay, are there any questions for Sheel?
Can you tell me something new about perfect complexes on that singular thing?
Something new about perfect complexes.
On a singular space, they're perfect complexes.
They are. That's right. That's right. Yeah, I'm not sure I can tell you something new about perfect complexes. In fact, I would say most of the information is flowing the other way right now. We're using what we know about perfect complexes. For instance, on a proper singular space, they're dual in some sense to coherent complexes. So perfect complexes are some finite dimensional modules over coherent complexes, and these types of properties are very useful for us. But I'm not sure I have something new about perfect complexes to say. Thanks.
Can I ask a question about your theory of this Liouville sectors interacting with the homological mirror symmetry? You demonstrated an example where you got the mirror. Well, you decompose the torus, removing 3 points into smaller pieces, and it matches the mirror.
Yes.
Precisely. And how general is that phenomenon?
That's a great question. I don't think we know how general it is at the moment. I mean, we have heuristics that do it in some number of cases, and there's some work in progress to try to write down some general story for that. But right now, I don't have a completely general proposal. One can conjecture that in all these cases where the mirror is naturally some singular normal crossings variety, and you can see the mirror construction naturally on it, then you should see the sectorial decomposition. The problem with implementing that is actually the mirror construction for such things is a bit indirect. It sort of doesn't directly, if you think of this nodal elliptic curve, we're used to thinking about mirror symmetry in terms of torus vibrations, right? So you could try to put some circle vibration, but then you have these pinch points where everything collapses, and it's some sort of singular fiber, but it's a little bit different than the usual type that arise in, say, the Gross-Seibert program.
More questions? Okay, well, if not, let's thank our speaker again.
Thank you.